Welcome, everyone. I am so excited to put on my professor hat today and guide you through this explainer on one of the most pivotal modules in your coding journey, C Piscine 09. If you're feeling a little overwhelmed by the sudden jump in complexity, seriously, take a deep breath. You are in the exact right place. My goal today is to walk you through these exercises step by step, unpack the underlying logic, and give you the specific tips you need to not just pass the assignment, but genuinely understand the mechanics working under the hood.
Here's our syllabus for the session. We'll start with Part 1, the toolbox, which covers Exercise 00, then Part 2, the blueprint, where we tackle Makefiles. Part 3 is the boss fight, taking on ft_split, and we'll wrap up with some final professor tips to guarantee your success.
All right, let's dive into Section 1, the toolbox, Exercise 00 libft.
I want you to think of building libft not just as another assignment, but as forging your very own reusable toolbox for all your future C programming. To build this toolbox, we first need to understand what a static library actually is. Up until now, you've probably been compiling individual .c files one by one, right? Well, a static library is simply an archive file. It ends in .a that bundles a bunch of compiled object files, those your .o files, into a single highly reusable package. This is a massive time saver. Instead of compiling your favorite functions from scratch every single time you write a new program, you just carry this compiled toolbox with you.
So, what exactly is going inside this toolbox? For this exercise, you have to recreate 5 standard C functions entirely from scratch. You'll be building ft_putchar, ft_swap, ft_putstring, ft_stringlen, and ft_stringcompare. And remember the golden rule here: the only external function you are allowed to use is write. These 5 clones are going to serve as the rock-solid foundation of your new libft.
Let's act like we're at the whiteboard right now. How do we actually construct this library using a shell script named libft_creator.sh? There are exactly 3 essential shell commands you need. First up, you run cc with your standard flags, wall, wextra, werror, along with the -c flag on your .c files. That -c is absolutely vital because it stops the compiler before the linking phase, generating those object files we talked about. Second, you use rrc libft.a on those object files. The R command stands for archive, and this is the magic command that actually bundles everything together into your library. Finally, you run ranlib libft.a. This indexes the library, making it way faster for the compiler to look up your functions down the road.
Okay, so you've written a shell script to do this manually. But let me ask you a question. As your projects inevitably grow from 5 files to 50 files, do you really want to rely on a simple brute force shell script every single time? How do we intelligently automate this entire construction process?
That brings us perfectly to Section 2, the blueprint, mastering Makefiles.
Let's do a quick comparison between manual compilation and using a Makefile. Manual compilation is honestly just tedious. If you change a single line of code in one .c file, a standard shell script is going to force you to recompile every single file all over again. Makefiles, on the other hand, are incredibly smart. They are dependency-based. A properly written Makefile checks the file timestamps and only recompiles the specific .c files that were actually modified. It is essentially the ultimate architectural blueprint for efficiency.
Let's break down the exact rules your assignment demands. A Makefile works by defining very specific rules. The all rule is your default setting. Running make, or makeall, compiles your entire libft.a library. Then we have clean, which you could think of as your housekeeper. It strictly sweeps away the temporary .o object files. But then you have the fclean rule, or full clean. Think of this as your nuclear option. It runs clean, but it also forcefully deletes the final libft.a binary itself. Finally, there's re, which stands for rebuild. It runs fclean to wipe the slate entirely clean, and then immediately runs all to build everything fresh.
Now, I need to put my strict professor hat on for a second. File paths matter immensely in this exercise. Your source files absolutely must reside in the srccs folder, and your header file ft.h must live in the includes folder. Because they are separated like this, you have to explicitly tell the compiler where to look for your header. You do this by adding the -i includes flag during compilation. If you forget that flag, your compiler is going to throw a fit and say it can't find ft.h.
And speaking of strict rules, check out this quote directly from the guidelines. Avoid using wildcards like *.c, as they are explicitly warned against in standard Piscine projects. I know it is incredibly tempting to take a shortcut here, but you really have to explicitly list out your source files, ft_putchar, ft_swap, and the rest inside your Makefile. It's a great habit to build now.
All right, you have your toolbox, and you have your automated blueprint. Now, are you ready to face one of the most critical, notoriously difficult algorithmic challenges in the entire C Piscine? Take a quick sip of water, and let's get focused.
Welcome to Section 3, the boss fight, conquering ft_split.
I know this function has quite the reputation among students, but we are going to break it down logically, step by step, until it makes perfect sense. First, let's define our end goal. What exactly is ft_split doing? It's a function that parses a main string and chops it up into smaller words using any character found in a provided charset string as a separator. It then returns an array of string pointers. If you've ever played around with Python's split function, this is basically what we are recreating in C completely from scratch.
Let's look at how this logic actually builds dynamically. Because we have no idea what the size of the string is beforehand, we have to use a multi-step dynamic memory allocation process with malloc. Step 1, you have to iterate through the entire string just to count how many valid words exist. You use that count to malloc the main array of pointers. Step 2, iterate through the string again. When you hit a valid word, find its specific length. Step 3, malloc enough memory just for that specific word's characters. Step 4, copy the characters into this new space and store that new memory address back into your main array. It's like a giant puzzle coming together.
Now here is the absolute most important professor's memory tip I can give you today. Always add +1. When you malloc the main array in step 1, you must allocate room for your total word count, +1 for the final null pointer that signifies the end of the array. And in step 3, when you malloc space for a word, you must allocate the word's length, +1 for the null terminator, the \0. If you forget these +1s, you are going to be greeted by every C programmer's worst nightmare, a segmentation fault. Don't say I didn't warn you.
You also have to be very careful to handle the edge cases. The instructions state you must draw your conclusions accordingly, which is a fancy way of demanding strict logical thinking. What if the string starts with separators? What if it ends with them? What if there are 5 separators right in a row? Your algorithm needs to gracefully skip over all of these. There can be absolutely no empty strings in your final array.
Let's move on to Section 4, Final Professor Tips.
You did fantastic sticking with me through all that logic. Let's review your core takeaways from today's explainer. First, really embrace libft as your personal, reusable toolbox. It is going to be your best friend in future projects. Second, use Makefiles to smartly automate your builds and respect file dependencies without relying on wildcards. Third, never let complex algorithms like ft_split intimidate you. Just break them down into smaller, logical steps. Counting, allocating, copying. And finally, double-check your memory allocations for that crucial +1 and rigorously test your edge cases. You have accomplished a ton today just by wrapping your head around these concepts. You've built the toolbox, you've drafted the architectural blueprint, and you've conquered a notoriously complex algorithm. The true foundation of C programming is now firmly in your hands. So I leave you with this question: what incredible programs will you build next? Keep coding, keep experimenting, and I will see you all in the next session.